our next module, our topic is about the last part of the introduction to computer architecture. So here we will be discussing some of the base or the foundation of the computer architectures. So why do we have to study computer organization and computer architectures? So we have to study it in order for us to be able to design better programs, because knowing how a computer is organized, or how a computer is actually made up of, what are the interconnections between the elements in, or the components and the functional units in the computer system architecture, will help us define how we throw, or how we want our data to flow. So it includes system software such as compilers, how our compiler should react into the functional units depending on how are the interconnection, or how is the system or the computer system built. So it can help us optimize program behavior, um, knowing the pasikot-sikot of um, the functional units will help us optimize how we want our program or instructions to be designed and programmed. So it will help us also to evaluate computer system performance. If we have lesser memories, and if we have memories that are dedicated or attached with the central processing unit, then we can evaluate the computer system performance based on how it is constructed, and understand time, space, and price trade-off. Will increasing the memory, or the capacity of the memory, affects the price of the computer, which is more reasonable in terms of price, increase more the capability of the memory, or the capability of the processor. Do we have to deal with multi-cores or multi-processors? So those sort of things uh, should understand and be able to know that, in order for us to deal with how we can design and how we can deal with computer systems. So it may be helpful in when we get into the industry, or even if we're just building our own computer systems. Now, definition for computer organization is um, answers the question, how does the computer works, or how does the system works. So we must be familiar with how various circuits and components fits together to create a working system. Who is connected into this one? Who should be situated next to this one? Who is uh, not working without this one? So those sort of things. So computer architecture, on the other hand, focuses on the structure and behavior of the component of the computer. So how should memory unit behave when ALU throws a data to him? Who will fetch the data? Yeah, so some sorts of these things. So computer architecture includes many elements, such as the instruction set architecture. We will briefly discuss it, though there are separate modules or lessons for the instruction set architecture. So we have the operation codes. It includes the data types, what kind of data can be accommodated by your computer system based on the architecture. So what types of registers are included in your um, computer system? Does it have a cache? Does it have a special purpose registers, or does it just have a memory and straight to the processing unit? What are the addressing modes it can accommodate? What are the main memory access methods? What are the IO mechanisms? So those things that we will discuss more in different modules of this subject are included as part of the topics in the computer architecture. So it mainly answers the question, how do I design a computer? So the computer architecture for a given machine is the combination of its hardware components plus the instruction set architecture of that component. So we will introduce at least a brief definition of the ISA later. Now let's focus on what is a computer architecture, because under in this module we will be discussing about the foundation computer architectures that has been the basis of our computer architectures that we use today, or our computer systems that we use today. So computer architecture, by definition, it refers to the attributes or characteristics of the system that have a direct impact on how it will function. Yung we We can think of it as yung lahat ng considerations and characteristic na may impact doon sa logical execution of the program. How does this do this? Bakit ito siya yung next na functional unit? So things like that. So this includes the description of the computer system's instruction set architecture, and then ilang bits ang kayang i-represent ng mga data type mo. Kaya niya ba yung integer? Kaya niyo ba mag-long integer? So those types of things are to be considered in determining or choosing a computer architecture that you wanted your computer system to follow. Ano ang mga memory addressing techniques? So those are the things that I've even mentioned earlier. So computer organization, on the other hand, are the specifications of things such as control signals, interfaces between computer and peripherals, sino yung magka-connect dito, anong connection, anong nagko-connect sa kanila, bakit sila magka-connect, and the memory technology being used. Gagamit pa tayo ng cache, bakit kailangan natin gumamit ng registers, anong kailangan registers natin, kung ganito ang purpose ng ating computer system. So, those computer organization. Basically, computer organization ay titingin lang sa kung paano ang arrangement, basically just the word organization, so the arrangement and how it is situated between each other. Pero yung logic na why they are situated, why they are connected, ay under na ng computer architecture. So, we can simply set their difference that architecture is attributes visible to the programmer. Paano mo i-handle kung ganito ang arrangement nito. Organization is how features are implemented. So, I have in the module, and I will flash here this figure. So, computer architecture is the design of the abstraction layers. Ano yung ibig sabihin ng abstraction layers? So, you can see here that there are this in purple color are the abstraction. Pag sinabi natin abstraction, we are trying to hide something that is unreadable or the ugly part of the computer. We are hiding the ugly part of the computer, interfacing it into or rather mas naiintindihan natin. So, ano yung mas naiintindihan natin? Mas naiintindihan natin yung application. As programmers, we can do the programming, the coding. We can do the algorithm. That's somehow an understandable part for us. Pero what we don't understand na, though we set the rules and we set them to do this, but what is the ugly part and we don't want to deal with it is the part after the algorithm, which is the programming language. The compilers, nandiyan na yung kung paano niya i-convert into binary, the instructions that are set into the codes of the programs, what the algorithm means in terms of binary. Yan. The programming language, the operating system, paano ibabato ng programming language, ipapa-interpret dun sa operating system na ito pala yung instruction na gusto kong ipaprocess. At sambutan na anong instruction set architecture, ano naman ang gagawin mo, anong uunahin mo, add, multiply, load, store, and sorts. So what is the architecture, paano natin transfer to, ano yung circuitry ng iyong system. So those are the ugly part of the system that we have to abstract kasi hindi natin nais na unawain pa yun at hindi na natin kailangang unawain because the computer itself will do the job. That's why there are computers, siya ang magdudo ng job. We are here to instruct, they are here to process and do it. So that is the abstraction, the layer na ina-abstract natin. Sila na bahala doon. So, and it outputs the devices na pag-outputan ng results ng ating in-instruct via the programs and the algorithm. So now, before we get into ano ba yung von Neumann architecture, actually discuss ko na siya, hindi ko lang mention that it's actually the von Neumann architecture. I masked it into what a computer should look like. Parang ganun. So let me go back in time during the mechanical era. I've mentioned that the ENIAC, ang kanyang advisor is von Neumann. Right? I've mentioned it. So it's actually in the time of the ENIAC that von Neumann have um, have conceptualized this should a computer look like. This should be the functional unit. This is the interconnection that we are expecting when we are trying to build or conceptualize a machine. So from the ENIAC, so he advised the designs of the ENIAC, though he's not the main creator, or he does not, hindi siya yung main nag-conceptualize sa ENIAC. Now, von Neumann actually became interested with so there are marami na naging inventions of the computer machines or the computing machines. Mas naging interested siya sa how we can speed up the computational problems. As mas naging interested siya dun other than adding more power or more functions dun sa what it can compute. Mas naging interesado siya sa how you can speed up the computations, because yun yung kailangan na unang resolve ba, other than adding more capabilities of the computer. Paano mo muna mapapabilis? Kasi when it speeds up, mas marami ka ng opportunity to add more functions or kakayanan, capability of your system. Now, when he learned about the ENIAC, he became a consultant and advisor for it, and na parang nagkaroon siya ng idea of its logical structure dun sa technology na ginagawa niya, and nagkaroon siya ng comparison between the ENIAC and the analytical engine. So na realize niya, or dun sa pagkakatingin niya sa analytical engine, the data is stored in the memory. Yun yung concept na binigay ni Babbage. Tapos nung ginawa nila yung ENIAC, kasi hindi naman na-build yung analytical engine, so they've adopted that the data should be stored in the memory. However, the instructions are still based on the switches, mechanical switches pa rin siya, na like if I add, I will switch this one, kaya magkakaroon ng add, though the memory is stored in there, the instructions is still manual. Kung matatandaan ninyo, and I think na-i-discuss naman ito sa inyong computer fundamentals, nung panahon na yung programmers, panahon ni na Ada Lovelace, she is actually the first programmer, at she worked with Babbage doing first intentions nila to perform programming. So she's actually the first programmer, pero yung coding niya doesn't come in the form na sa ating pagko-code ngayon na tinatype natin tapos nira-run and then there's a compiler. Yung kanilang programming dati is they are just turning off and turning on the switches. Yun yung programming in that part. Like if I turn on this will function. If I want to add, I will turn on these switches and this will function. So yun yung programming on the early days. So the instructions are based on setting the mechanical switches. Yun. So, yun yung nakita ni von Neumann sa pag-work niya sa ENIAC and sa analytical engine. Data is stored in the memory, instructions are from the switches. Kaya sabi niya, bakit hindi na lang mag-reside both the instruction and the data into the memory para yung instruction is stored na din. Hindi na kailangang manual na click on and off switch. No. Yun yung gusto niya i-eliminate. So, this represents the innovation and revolution that comes up with the von Neumann architecture in computing. So, yung dinescribe na architecture ni von Neumann dun sa introduction ng kanyang concept ay na-discuss na natin. It includes 5 units, which is the input device. Sabi niya, a machine, the architecture of a computer should have an input device. There is a memory unit that holds the instruction and the data, and there is a central processing unit that processes the instruction and the data, and an output device that will display or will accept the results that the users need to see. So computers with the von Neumann architecture are those computers with single memory. So both data and instructions are handled by the memory. What you can see in each memory cell is a combination of both data and both instructions. So, yeah, by definition, ulitin natin para mas ma-familiarize ulit tayo. By definition of von Neumann architecture, ang kanyang brain and heart, yung pinagmumula ng kanyang processing, is the central processing unit. It has the ALU and the control unit. The ALU performs all the operations that's needed. Siya yung nag-ooperate. And then the CU controls the flow of the data and the instruction. Kanino pupunta yung data na to na kinompute, kailan ko ako magpapasa ng ng operand or ng operation kay ALU para alam niya kung ano i-compute niya, kasi si ALU hindi na siya responsible sa kanino ka bibigay ng sagot ko. No, basta sa kanya sasagutin ko lang yung pinapagawa niya ni CU. Kung ano lang ibato mo sa akin, ipa-perform ko to mathematically, bahala ka na. So si CU bahala dun sa mag-manage ng mga data that flows between all the functional units. So the constant interaction happens between the CPU, the central processing unit, and the memory unit. So the input, pagka-input niya, once lang siya sa memory siya pumupunta. So the input unit, once lang siya. So kung makikita natin, the input unit or input devices are may isa lang siyang arrow that's going into the central processing unit and the memory unit. Pero meron dalawang arrows vice versa sa central processing unit and the memory unit. Ibig sabihin, there's a continuous interaction between the two. It can send and retrieve data both ways. So the memory unit can give data to the CPU and it can get data from the CPU. So the CPU can give data to the memory unit and can get data from the memory unit. So ganun kasimple yung interconnections between these functional units. So the stored program model. So the earliest computing machines have fixed programs. So ibig sabihin, computers were designed for specific purposes, for simple purposes. Pag sinabing census, for census sila. Parang ganun. Pag sinabing calculator sila. So that way. So it can do earlier computers can do basic mathematics, but it cannot be used as word processors, hindi pa, at least not in that time. So changing the program of a fixed program machine requires rewiring, reconstructing, or redesigning the machine. So we cannot use, kumbaga ang ibig niya sabihin, if a computer, an embedded computer, if you want it to function more than its task to do so, then kailangan mong i-modify. Kailangan baguhin mo yung wirings niya, yung interconnections niya, yung structures niya. So, ganun kasimple. If one is dedicated into one task and you want it to do another task, then rewire, restructure, reorganize, and reprogram. Now, that is a laborious process. Yung, kung gusto mo, itong machine na to, ko-convert mo sa ganito, and you have to redo it, rewire, reprogram, do it all over again. It was a laborious process. So that was back then, kasi sa kanila gumagawa sila ng machines dati, nag-invent sila ng machine for a specific purpose. So one task, one machine, parang ganun. So what the stored program computer architecture or change in that concept is that, sa idea niya is, bakit kailangan kapag iba-ibang task, magre-rewire na naman tayo, magre-redesign ka, magre-reprogram ka, bakit hindi ka nalang mag-install ng kailangan mong operations para kahit iba-iba yung instruction na iutos sa'yo, meron ako niyan, teka, ano pinapagawa mo sa akin? Meron ako niyan, ito, magagawa niya. Hindi yung isang instruction, isang set of instruction lang ang meron ka, isa lang yung task na magagawa mo. Kaya pag hindi ka na kailangan at may iba na silang mas kailangan, ang gagawin sa'yo, babaklasin ka, i-redesign ka. Parang ganun yung naging issue. Kaya sabi, yung sa stored program computer, ako, ibang gagawin ko. Ako, kasama sa design ko, I will have a set of instruction para marami ako nagagawa. Kung limited man to, then they can add another set of instruction that I can do. So, anong gusto mong pagawa sa akin? Gusto mong addition? Yeah. Ito yung set of instruction ko for addition. This one's my set of instruction for multiplication. So, the stored program computer includes an instruction set that is stored in the memory para pag meron kang kailangan, available siya and you don't have to rewire and restructure and reprogram the computer system. So, which is, ganun din yung mga computers natin. Ngayon, ganun na rin yung idea. Meron tayong built-in set of instruction that it can perform. Kaya kung makita nyo, meron mga laptops na kayang gawin ito. Bakit itong isang laptop hindi ito kayang gawin? Kasi kahit na sila, dahil dun tayo matitingin sa ano yung ISA, ano yung instruction set na naka-include sa'yo. Now, a von Neumann architecture is actually a single instruction, single data type of computer system. So, later, I will introduce the Finn's taxonomy. Ano yung single instruction, single data? So, just for the description of the von Neumann, let me mention kung ano yung single instruction, single data, or SIST. Okay. So, a single instruction and single data type of computers are the processor that accepts, or there is just one way, parang isa lang yung daan or stream for data and instruction. Kumbaga parehas ng data path yung instruction and data para sa computers na to. At ganoon ang von Neumann architecture. For a single processor, siya ay merong isang daanan for instruction and data. Ibig sabihin, if they are passing through the data flow, the instruction and data both uses the same data stream. Kumbaga, the instruction and data are using both streams into the processor. So, what are the key features of the von Neumann architecture? So, the major one is that there is no distinction between the data and instruction, since both data and instructions reside in the same memory. Diba, nabanggit natin kanina. Na ang naging innovation niya is the instruction, dati data lang yung nagre-reside sa memory, now the instruction also resides in the memory. However, they are both residing in the memory. Now, they are not actually, hindi naman sasabihin ng memory na, kilala ko sino dito ang data, sino dito ang instruction. No, they are both treated as laman. So, regardless if you're a data and instruction, basta alam niya may laman siya. So, there is no distinction between what is a data and what is an instruction. You are both elements of the memory cell, contents of the memory cell. So, these have several implications. So, instructions are represented as numbers, just like the data themselves. So, they have both representations. So, the uniform treatment of instruction and data simplifies the design of memory and software. So, it's actually a pro that na walang distinction yung data at instruction. Kasi parehas lang yung treatment sa kanila. Mas simple yung design. You don't have to classify, hindi ka magkakaroon ng another mechanism or other program that you need para sa which one I can identify as data, which one I should identify as instruction. Since they are both treated the same, you don't have a needed additional design to separate them. Kahit na totoo, they are two different things, or should be treated differently. So, instructions or data are not stored in separate memories. They reside, gaya ng banggit ko, they reside in both memories. Thus, they are occupying a single path. Kung makita natin dun sa ating diagram, ang memory unit natin may isang arrow papunta sa central processing unit at may isang arrow din pabalik naman sa memory unit. So, wala kang nakikitang dalawang arrow na papunta sa central processing unit at dalawang arrow na pabalik sa memory unit. Ibig sabihin, ang data at ang instruction ay parehas na sa isang arrow dumadaan. Parang ganun. So, isa lang yung kanilang stream na pinagdaraanan. Now, mamaya makita natin ano naman problema doon kung parehas lang sila ng daan, ng stream, ng path. So, the memory is addressed by location regardless of the type of data at that location. So, by default, instructions are executed in sequential manner in which they are present in the stored program. So, one of the problem in the von Neumann architecture is we call it the von Neumann bottleneck or the memory bottleneck. Kung ma-research niyo, other term is the memory bottleneck. Ano yung memory bottleneck? So, the problem of the memory bottleneck is it presents a limitation of how fast the processor can process data. Bakit? Kasi imbes dahil isa lang yung path ng instruction and data, kapag may instruction na dumadaan dun sa path, a data cannot pass into it. Kuga, hindi sila pwedeng magsabay kahit na ang kailangan sa instruction, kailangan ko ng isang data. So, ibig sabihin, hindi pwedeng magsabay na si instruction. Kunyari, I would like to add 3 and 5. So, hindi mo pwedeng sabay na dumating si 3 plus 5 para isang bagsak ng processing na lang. Hindi. Pag instruction ng inuna mo, kunyari, I'd like to, ang inuna mo muna i-data, 3. Siyang unang dumating. Anong next? Plus. Anong next? 5. So, ganun. So, sequential at utay-utay or per single ang dating ng gamit sa ALU, parang ganun. Parang, how do I say it? Kumbaga, ang gusto sana, kung ikaw yung mekaniko, ikaw yung ALU, ang gusto mo sana mangyari is pag dumating yung kotse, nandun na kasama yung toolbox. However, dahil isa lang yung path na daraanan ang nangyayari kung ako yung mekaniko. So kung sabay na dumating yung kotse at yung toolbox, pwede ko na at that moment na dumating yung kotse kasama yung toolbox dahil nandun sa kanya, then I can start processing. I can start fixing it and repairing it, right? Now, ang problema, dahil ang von Neumann ay kumbaga sequential, hindi pwedeng sabay kasi isa nga lang yung kanilang data path. So, pagpunta ng kotse, pagpunta ng tao, hihintayin pa niya yung kotse, hihintayin pa niya dumating yung toolbox, saka pa lang siya makakapag-perform ng process. So, ganun. So, that becomes a bottleneck. So, it limits how fast the processor can run kasi there are waiting times, there are idle times for the processing. Though, busy siya sa pagkilala, this is 3, this is plus, this is 5. There are idle time for the processing. So, instruction and data must share the same path to the CPU from memory. So, if the CPU is writing a data value out of the memory, it cannot fetch the next instruction kasi ang handle pa niya ay si 3. Si 3 pa yung gumagamit ng path. So, the next instruction can be executed once tapos na siyang mabasa si 3. So, ganun. It must wait until the data has been written before proceeding and vice versa. So, ganun. Yun yung naging bottleneck. So, dahil isang daan lang ang nadaraanan ng data at ng instruction, kailangan maghintayan bago matapos ang isa makilala ng CPU. So, we need multi-level caches to reduce the miss penalty, and memory systems should be designed to support cache with burst mode accesses. And we will further identify what this is pag nandun tayo sa memory organization. Ano ibig sabihin ng mga to? Now, let's go to another type of foundational computer architecture, maybe. We'd like to call it universal Turing machine. I don't know if heard na ninyo, maybe it was discussed kung ano yung Turing machine. So, Turing machine is from Alan Turing. Siya yung nag-conceptualize nito. So, it is finite sa automata ko to nakilala, though hindi pa ako nakakita nito, pero yung how it works na-discuss namin to nung nag-automata kami. So Turing machine is actually consist of a tape tapos reader, pagbasa ng tape. Yan. Tapos may memory din naman ito. Now, the tape begins with the input of the machine written on it, surrounded by infinitely many blank cells. Kung makikita nito dito, para kang merong, yan, this one, the tape here. Tapos, yung tape na yan, parang may imagine nyo, may mga, imagine nyo, this one. So, ito yung isang tape. Kunyari na mapa pa to. Meron itong cell dito, cell 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each memory cell can contain values such as 1 and 0. Binary lang to ha. So, 1, 0, 1, 1, 0, 1, 1, 1, 0, or blank kapag wala pa siyang input. So, depende sa input mo. Kung input may 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, so, yun yung laman ng tape. So, paano siya gumagana? Actually, it's made up of states. So, kapag get focus it. Yan. So, we have this laman ng tape. So, kunyari, different cells na yan. Cell 1, we have the 1, 0, 1, 1, 1, 0, 0, 1, 1, 0. So, these are the input. So, when the reader read this, pag nag-move yung cell, babasa niya yun. Input ay 1. No, sorry. The first input that it's gonna read is this 1. Kasi ito yung papasok. Kunyari, pag ganito ang pasok. Yan. 0, 1, 1, 0, 0, 1, 1, 1, 0, 1. So, how does the Turing machine works that way? So actually, it functions in a state transition diagram. Kunyari, the Turing machine is designed such as yung algorithm niya is ganito. O, ganito yung state transition diagram na naka-program sa kanya. So, kapag meron tayong input na ang una niyang mababasa ay 0, ang starting niya ay si S1, sa state number 1, wait lang, sorry, sa state 1, so pag babasahin ko na lang so ang una niya ay 0, so 0, ibig sabihin pupunta siya kay S2, 0, 1, S4, then 1, S5, pupunta siya kay S5, then 0, pagdating kay S5, actually dead end na. So, mali yung ginawa kong input. So, pag wala na siyang mapuntahan kasi wala nang arrow na palabas kay S5, that's a dead end. So, magkakaroon ng error. Yung input mo doesn't match the state diagram, state transition diagram. So, that is an error in the part of the Turing machine. Sabihin natin, meron tayong 0, 1, 0, 0. So, our last state is S1. So, our answer is S1. So, yun. Parang I don't know if you understand, but I hope na medyo nagigets ninyo yung kung paano nag-work yung Turing machine. Now, so it writes a symbol to the tape cell under the tape head, and it changes its tape according to the input. So it moves the tape head to the left or to the right. So pwede siyang mag-move either way. Kaya kung makikita natin, merong siya sa kanan at saka sa kaliwa na source ng tape. So it can move both ways. Now, Harvard architecture. So the Harvard architecture is the other architecture na usually covers this ng von Neumann. So what is the Harvard architecture? This nung nakita niya that the problem with the von Neumann is that both data and instruction resides in the same memory, thus have to deal with the single path going to the central processing unit. Yan. Nagkaroon siya ng idea na, why don't we, what we do to innovate and improve the architecture of the computers is to get a separate storage, magkaroon pa rin tayo ng memory, nakastore pa rin ang instruction sa memory, pero separate storage na for that. So there's a separate storage for that, thus there's a separate signal pathways. So may separate path na para sa kanila papunta sa CPU. So separate ways for the instructions and data, separate memory and separate path. So the modern computers actually now are somehow adapting into the Harvard architecture, wherein the processors now have two separate cache or memory, other types of memory kapag napag-aralan natin sa memory organization. So there are two separate cache na ikaw yung cache para sa instruction, ikaw yung cache para sa data. Thus, they can simultaneously be getting into the CPU for processing. So, Harvard allows two simultaneous memory fetches, one for the data, one for the instruction. So, does it improve? Yeah. Does it, kumbaga, it gives at least a solution to the memory bottleneck na inintroduce ng von Neumann. So, the Harvard architecture for streaming data has greater memory bandwidth, different memory bit depths between instruction and data, and more predictable bandwidth. So today, most processors implement such ways. Yung magka-separate yung signal path, separate din yung cache or the memory. storage for the instruction and the data. So, for performance reasons, yung kanilang naging reason. Here in Harvard architecture, there's no need to make two memories share characteristics. So, identified kung alin ang instruction, identified kung alin yung data. So, Flynn's taxonomy. So, ito yung na-mention ko kanina na mali-discuss natin. So, what is the Flynn's taxonomy? It's a system classifications that is proposed by Michael Flynn na nag-identify kung anong klaseng stream ang meron sa isang computer architecture, kung kung anong differentiation ang meron para sa pag-store at pag-operate ng instruction and the data. So, merong apat na class para sa na inintroduce si Flynn's taxonomy. Una is single data, single instruction, single data. Ibig sabihin, there is a single stream for the instruction and the data. So, parehas ang signal pathways for the instruction and data. Ganyan nga yung von Neumann. Meron din tayong tinatawag na multiple instruction, single data. Meron din tayong single instruction, multiple data, at meron tayong multiple instruction and multiple data. Let us try to define each class in Flynn's taxonomy. So, SIST. So, a sequential computer which exploit no parallelism. Ibig sabihin, walang magsasabay doon sa dalawa. Parehas silang naghintayan, sequential. Kapag may nagamit na ng instruction, ang data path, daga ka nagda-data path, ang pathway, then the data can follow kapag tapos na yung sa instruction. Yun dun lang niya magagamit. So, no parallelism, one at a time. So, example nga na yung von Neumann are old machines or old mainframes. Now, single instruction and multiple data streams. A computer which exploits multiple data stream against a single instruction stream to perform operations which may be naturally parallelized. So, for example, an array processors for GPU. Anong ibig sabihin ng single instruction, multiple data stream? So, nag-introduce sila ng mas maraming stream para sa data kasi usually sa isang set of instruction or set of process, ang meron tayo ay isang instruction at dalawang data, 3 plus 5. So meron tayong isang instruction right there and we have two sets of data. So usually there are more data that should be needed for processing than there are needed instructions. So sabi na we can include one data path or one pathway, one stream for the instruction and multiple for the data. So, yun yung include niya. So, multiple instruction and single data stream, on the other hand, multiple instructions operate on a single data stream. And it is an uncommon architecture since sabi ko mas usually common yung instruction na mas marami yung data kaysa sa instruction. So, why having it multiple, mas marami yung stream o daanan mo para sa instruction tapos isa lang yung daanan mo para sa data. So it is usually used for specific task as fault tolerance. So such systems, mga ganitong system. So the last class is the multiple instruction and multiple data stream. So multiple processor simultaneously executes different instruction and different data. Usually, this type of architecture ay multiple processors na or multiple cores na parallel na meron na silang kanya-kanyang task to perform na kayang pagsabayin yung instructions at the same time. Kaya niyang mag-accept na, ako muna mag-process to. Magsabay tayo magpa-process ng different instructions. So, yun yung multiple instruction and multiple data. So now, for the next module is actually the start of the next unit, which is about the assembly language. So in the next module, we will be discussing about the data representations, how data are represented, and I am assuming na marunong na tayo ng conversions from different number systems, maybe. Though it wasn't much discussed naman, wala naman tayo masyadong competition dito. So register sets and assembly language and assembly instructions.